In this video, we will learn about the low pass equivalent of a band pass signal. Well, we will cover this topic, but the main terms, if you observe in this title, the low pass signal and the band pass signal. So these are the key terms of our topic. So we will discuss the low pass signals and the band pass signals first, and to understand these two types of signals, then we need some basic knowledge from our undergraduate course. I'll revise those concepts, the basic concepts which are required to understand for these band pass signals and its low pass equivalent. So I will go through some of the basics we need from the concepts of signals and systems. Here, if you see, so I will revise those concepts before going to the topic of finding out the low pass equivalent of a band pass signal. So if you observe in this figure, in this slide, there are two more figures are shown here. If you see here this figure, it gives you x of f, right? It's the signal, the frequency response of a signal, and actually this solid line, this shows the magnitude response of the signal, the magnitude response. So the or we say the amplitude spectrum. If you want to draw the amplitude spectrum, the magnitude response or the amplitude spectrum, it is drawn like this. For different, see it's a continuous axis, right? F axis. So we have an F axis, the frequency axis, and this is the magnitude response. If you observe the phase response, because it's a real signal, the phase response is something like this, just shown here. So the amplitude response and the phase response, these two are actually important to get details of the signals. So we have the and you are familiar with these amplitude spectrum and phase spectrum from your undergraduate course. I'm just recalling it for this topic, just to recall it and to understand our today's topic, which is to find out the low pass equivalent. So if in the first figure we have the a signal whose bandwidth, this is known as the bandwidth, the positive frequencies, right? The positive frequencies, this is known as the bandwidth of this signal. So this is actually these positive frequencies are the bandwidth of the signal. If you observe the signal, it is the frequency components of this signal x of f is around 0, right? It's around 0. So it's basically a low pass signal. It's basically a low pass signal. Mostly the speech signal, if you observe your signals, those are low pass. For example, your speech signal is a low pass signal. So for a low pass signal, the frequency, the frequency contents are low frequency contents. So for a low pass signal, the magnitude response is located near 0, right? So this magnitude response, it's located near 0. In another figure, in the figure at the right side, if you observe the second figure, we have a signal which is known as the band pass signal. The reason for this to be a band pass, you can clearly see that it is in the uh, higher band. It is in the band of with the frequencies, the frequency components of this signal is located near f0, where f0 frequency, where this f0 is much greater than 0, right? 0 is somewhere here. So we will come to these signals. We will try to understand these in more details, but let's we actually we will try to find out the low pass equivalent of this signal, which is of interest, which is the also known as x positive of f. This one is known as x sub minus f, right? So our x of f has two spectral components. One is the positive frequency, all the components, all the x of x sub plus of f, which is the signal component, which is the signal part having all positive frequencies, while here the frequencies are negative, x minus of f. So we will see these definitions. We'll come to these definitions, and let's see these definition first. But before going to actually derive the low pass equivalent, let me go through some basic knowledge which is required for this topic. And first of all, I would like to give you some definitions of signals. So we would like to understand the signum function, which is signum of t, the signum function, and the signum function is defined as it's 1 for t greater than 0. Similarly, it's minus 1 when your t is less than 0, and it is 0 for t equal to 0. So this is the definition of the signum function. If you want to draw it, you can draw this signum function, and you can see on time axis, you can say, okay, my signum function is like this. It's plus 1 for all t greater than 0, and it's minus 1 for t less than 0. This is your origin. So similarly, you can define a signum function in frequency axis. It would be same, just you need to define it for f axis, right? So if you have a signum function in frequency axis, it would look like this. So you can say signum of f, signum function. So it's a plus 1, it's a minus 1. So we may use this one today. We would like to use the signum function in frequency domain. Similarly, you are familiar with the another signal, which is unit step function, and we would like to define our unit step function. As 1 for t greater than 0 and half when t is equal to 0. We define this unit step function, u of t, right? U sub minus 1 of t, and it's 0 for t less than 0. This is the definition of our unit step function. You can define a similar unit step function for frequency domain. Only instead of t you will have f, right? Instead of t you will have f. So you can have the unit step function in frequency domain as well. We will be using it, and you can define it for f axis, right? instead of defining, its definition would be same as this one. Just replace t by f, and you can draw it. Let me draw your unit step function for frequency domain. So if you want to draw it for frequency domain, it will be like this, right? A +1. We define it here. At t equal to 0, it should be half, and then there is a jump, and for greater than t there is it is +1. Similarly, for time axis, you can draw it for time axis or for frequency axis. So we will use these functions today when we try to derive the low pass equivalent signal. Let me recall some of the properties which are from Fourier tables. Actually, if you observe your Fourier table, you have the Fourier pair. If you see the Fourier table, you have cos of 2 pi f naught t. It has a Fourier pair, and what is the Fourier pair of this one? It's half delta f minus f naught, half delta f minus f naught plus half delta f plus f naught, right? So this is the Fourier pair. If you have a cosine wave, draw it properly. Let me draw it properly. If you have a cosine wave, something like this, right? Sinusoid, a cos wave. So if you have a cosine wave in time domain, right? It is in time domain. Cos of 2 pi f naught t. F naught is its frequency. In frequency domain, you have two delta functions. If you see, one is located at f naught, so you have an impulse here at f naught, right? And we have another impulse here at minus f naught. So we have delta f minus f naught, delta f plus f naught. Right? So this is your frequency. This is the frequency spectrum of your sinusoid or cosine wave. So we may use this spectrum as well. Another important property is the modulation property. If you multiply your x of t with e complex exponential 2 pi f naught t, so what happens to the spectrum of x of f? X of f is actually, it moves to minus f naught, right? So x of f is shifted to f naught. So we will see this property. It's known as the modulation. If you observe your table of Fourier transform properties, it's actually the modulation property. It's known as the modulation property. So we may need this property today in our derivations. Similarly, another Fourier pair is important, such as the Fourier pair for 1 over t. You may need this one as well. So if you have a signal in time domain which is 1 over t, it has a Fourier pair which is j pi signum of f. Now see, the signum function is important. You have signum function here. The Fourier pair for 1 over t is given by this pair. So we may need it today in our derivations. We will try to understand, but actually the signum function, if you observe the signum function, it's nothing but either it is 1 or -1. So if the frequency is positive, this is 1, so you will be left with minus j pi, and if the frequency is negative, it is -1, you will be left with plus j pi, right? So we will see this in details today. Now let me recall the one property of the concept, the one property of the complex signals. So if you see your complex signals, if you observe your complex numbers, actually, if you let me write it specifically with some example. You have, if you see your complex number, for example 1 plus j1, it's a complex number, right? So it has the magnitude of this number. Suppose this number is I represented by a complex number c. So it has a magnitude. What is the magnitude of this 1 square plus 1 square, right? So you have this is the magnitude, and you have the phase. You have the phase, which is tangent inverse of the imaginary component over the real component, right? So it has, in this specific example, it is 45 degrees, right? It's 45 degrees. Now if I change this plus sign, or if I say C conjugate, right, the conjugate of C, so what you do, you just change this plus into minus. This is the conjugate. Now when we take the conjugate of this number, what will happen? It doesn't change the magnitude. If you compute the magnitude of C conjugate, it's the same, square root 2 as C. But if you see the phase of this, if you see the phase of C conjugate, let me write it. If you see the phase of C conjugate, this is it would be minus tangent inverse of this part, which is -1, over the real part, which is 1. Now it is minus 45 degree, right? So the phase, by changing this sign, the magnitude does not change, only the phase changes. So it's actually, the phase is equal to the negative of C. So this phase is equal to the angle is equal to the negative of the 1 plus j1. These properties will be used today in our lecture, and let me recall one more property of a Fourier transform. If as I have shown you above, a signal which I said that it's a low pass signal, let me draw it over here once again. So if you have a low pass signal, your frequency spectrum is around 0. So it has the magnitude response, which is shown here in this blue color. It will also have the phase response, right? What do we mean by magnitude response and the phase response? If you observe the signal, this is x of f, right? Frequency domain signal. We would have the corresponding time domain signal, x of t. So if x of t is real, if this x of t is real signal, usually we have a real signal. So if this x of t, your speech signal, is just an example of a real time domain signal. So if your x of t is real signal, you would see that it's actually a low pass signal. It's a low pass. A real low pass signal would have the magnitude response which is located near 0 at the frequency axis, which means that these frequency components with these are the magnitude with these magnitudes. These frequency components with these magnitudes are the they can make up your x of f. If you have these, if I take some discrete frequencies, and with each frequency you can see, like for example this frequency, it has this magnitude. So its frequency means it's a sinusoid, a very low sinusoid, close to 0, maybe 2 hertz, 4 hertz, whatever it is. So 4 hertz or 4 cycles per second has this magnitude, right? So if you have 4 cycles, it's 1, 2, 3, 4 cycles. It has certain magnitude, actually, which will scale up its amplitude. It will scale up its amplitude here. It may be some value a, minus a, right? So this actually this corresponds to this scaling. If you go to the higher frequencies, such as this one, it has a very low amplitude spectrum. So its amplitude is very low. So magnitude response, right? So it's, if you see over here, it has a very, this frequency is, although it is a very high frequency, right? It may be very high frequency, such as like this, but its amplitude, if you see, it's low as compared to this one. So this is very low. This may be a over maybe 50, right? Plus a over 50 minus a over 50. So it's much lower as compared to the amplitude of this low frequencies. So lower frequencies has higher amplitudes as compared to the higher frequencies in this low pass signal. So in this low pass signal you have multiple frequencies. If you add those multiple frequencies with keeping in view these the amplitude which is given for each frequency, these are actually the Fourier coefficients which you determine using the Fourier series, right, or Fourier transform. So keeping in view these components, this actually translate to its scale, this sinusoid. So if you add all these sinusoids with different amplitudes, different frequency, different amplitude, if you add all these, it will make up your x of t, right, for a given time interval where this exists, this real x of t exists. So it has only these frequency components which are important. Now it has the magnitude response, and another is its phase response. As I told you, for a complex number we have the magnitude and the phase. So it has, each frequency has certain phase, and the phase response of a real signal looks like this, something like this. So if you observe the magnitude response, right, if you observe the magnitude response, it is an even function. See, the magnitude response is an even function. When we say it's an even function, what do we mean? That x of minus f is same as x of f. right? X of minus f is same as x of f. So if you this property can be find you can find this property in this response. So if you invert it, the mirror image, it will have the same x of f. It's both are the same. Now for a real x of t, the magnitude of x of minus f will be same as the magnitude of x of f, right? And the angle, if you observe the phase response, this is the phase response. This is the phase response. So you also you try to find out the phase spectrum, right? And for the phase spectrum, you are interested in the angle of each, the angle related to each frequency. So you have different frequencies and the angle related to each frequency, which you can find out in your Fourier series. So that if you find the phase spectrum, if you see this real signal, this is the spectrum for a real x of t. So for the real x of t, for the real signal x of t, the magnitude response, it has this property. It is an even function. We say it's a even function. It's an even function. While the phase, if you observe the phase spectrum for these frequency, it is positive while it is negative here. So, and it is actually the if you observe the phase here, the phase for these frequencies, for the frequencies towards the right side here, the phase for these frequencies is positive, and for these it is negative. And if you observe this function just as a function, if you observe it as a function, this is actually an odd function. So the phase response is an odd function. So this is for real signals. The amplitude response is even function, and the phase response is an odd function. So if you observe the angle, angle of your x of f angle, if you observe the angle, the phase spectrum, the angle of your x of f, it looks like this. So it is an odd function. Or in other words, we say that the angle of x of f is negative, or I should say x conjugate of f is minus of x of negative of x. So the angle of x conjugate of, now what is actually the conjugate? Conjugate I just showed you in the while using the complex number. Let me discuss it with the help of signals. So if you are interested in signals, because we will talk about the signals, so we are interested in finding out the conjugate. When you have a signal x of t, which is real, right? A signal x of t is real. So we say it has the Hermitian symmetry. We say when the signal is real, the Fourier transform of a real signal, the Fourier transform of a real signal x of t or it has Hermitian symmetry. We say it has Hermitian symmetry. Now, what do we mean by Hermitian symmetry? We say Hermitian symmetry means the we say x of minus f, it's equal to x conjugate of f. X of minus f is equal to x conjugate of f, right? And when we say it possesses this symmetry, by this we mean that the magnitude response of x of minus f would be same as the magnitude response of x of f, right? If you observe its magnitude response, it would be same, and the phase response of x conjugate of f would be minus the phase response of x. It would be negative of this. So we just saw the phase response of this signal x of f for our real signal, which is like this, right? So this is for x of f. So if you say the negative of this, so all the just invert the positive, these values will be. So if we want to draw it, the negative of this one, so you draw it like this. All the positive values would be negative and the negative values would be positive. So this is minus, it is this one. So I am drawing it here. The angles are negative, right? So this is the response, the phase response of x conjugate of f is minus negative of the phase response of x of f, right? So in other words, we say that it is the magnitude of x of f is even. The magnitude of x of f is even because see, the magnitude is an even function for a real. If it is real, fx of t is real. So the magnitude of x of f is real, even, and the phase is actually odd. The phase is odd. So a real bandpass signal, a real baseband signal. A real baseband signal looks like this. Which has the frequency component. It has its bandwidth W, and the frequency component. This is the positive frequencies. This is known as the bandwidth of this signal. Now we have positive frequencies. These are all positive frequencies, and we define this as the bandwidth of our baseband signal. It is a low pass signal. You need just a low pass filter to can give you this signal. Just it can pass through a low pass filter, right? If you have a low pass filter with this filter response h of f, your frequency, your low pass signal passes through a low pass filter. It can pass through a low pass filter. Now if you have a signal which is in higher band, this low pass signal would block it, right? So the term low pass, we say low pass or the baseband signal. This term is used for a signal which has lower frequency content. Right? These are the components of this signal. Now when we say the band pass signal, the band pass signal, usually we talk about the real signals, right? So we are always interested in the real signals because we transmit real signals, we receive real signals. So an example of a band pass real signal would be like this. You have a signal, I am just trying to draw an arbitrary shape. You have a real signal, right? You can draw it here as well, just a random shape. So you have a signal, let this be f0, it's around f0 minus f0, 0. So this is an example of a band pass signal. A band pass signal, it's also real. If you observe, you can see that it has the same it has the x of f, and if you observe this property, it possesses this property, x of minus f is same as x of f. It possesses this property, right? So it's, or we say the magnitude is same. So if when you take the mirror image, you will get the same x of f. So it has whatever is for the positive frequency, we have the same signal for the negative frequencies as well. So we have x of f, which is real signal. Now you can observe it to be real signal. You can observe this to be a real signal. Its magnitude response is given. It is if you take the magnitude response of this mirror image, or you take the magnitude response of this one, you get the same magnitude response, which can be seen from this figure as well. So the magnitude, see, for example, at frequency f0, whatever is the magnitude here, it's same as at minus f0. So if instead of f you put it f0, it will have the same response, same magnitude. And for each frequencies you will find this symmetry. So the magnitude response is, we can say that, okay, the magnitude response is even function. It is an even function. The magnitude response is an even function. And if you observe its phase response, the phase response would look like this, right? It would look like this. So the phase response is an odd function. The phase response is an odd function, right? So the phase response, for example, you can just observe it. You can observe it for at this higher frequency. It's positive. It's a frequency greater than f0 somewhere. It's positive. But at the same time, if you observe it here, it's negative, right? So here the value is positive, here it is negative. So it's an odd function of frequency. So the phase response is odd function. If you observe the phase of x of minus f, it is minus the phase of x of f, x of minus f, right? This is negative. Phase of x of minus f is minus the phase of x of f. We can say it would be like this. So it is an odd function of frequency. Now move towards the further define the positive frequencies and the positive spectrum and the negative spectrum of x of f. So if you observe the real signal, let me draw it here once again to define these terms. You have a signal, baseband signal, right? A baseband signal. So for a baseband signal, this side we say this is x positive of f, and this side this is x negative of f. These are the we define these positive spectrum by x positive of f, and the negative spectrum x negative of f. If you observe, because this is an even function, we can have this, we can always have this x negative of f. We can obtain this one from this signal, right? So if we just take a mirror image of this one, it's the same as this part, right? So it means, now if you are familiar with the modulation of this signal, if you have x of t which has this spectrum, x of t which has this spectrum x of f, right? X of f, and you modulate it, this x of t, e raised to power j 2 pi f naught t, you modulate it. So the spectrum moves to f minus f naught here, right? So the spectrum moves to somewhere here. So let me draw it. You have this spectrum over here, it will be at f naught 0, right? This is I'm just showing this one, it because it's a real signal, so you should have somewhere here as well, minus f. So just considering the positive frequencies. Now if you observe your signal, this bandwidth is 2 times the bandwidth of the baseband signal. If we modulate it, it's 2 times. Now we know that the information in this x positive of f is enough to reconstruct this signal, because we can always make this x negative, the other part, we can always make this other part from this one. So we would be interested, instead of transmitting a signal with 2 times the bandwidth, we will be interested in transmitting just this signal, because this is a redundant part now. If we transmit this signal from source to destination, right, we actually do not lose any information. So we transmit all the signal, we transmit all the information, because this x positive of f contains all the information, right? Now we would be interested to find out a signal, a baseband signal, whose passband spectrum is just this one. Like what should we transmit? What should be the baseband signal whose passband spectrum is just this one? So it's just saving your bandwidth, just W. You'd be interested to transmit only the signal with W band instead of 2W, which is twice, and bandwidth is very important source of communication. So we will in our lecture today, we will try to find out the x plus t equivalent whose Fourier transform is x plus f. We will try to find out this signal, right, which can be transmitted and its bandwidth, it would transmit all the information of x of t. It would transmit all the information of x of t, and its bandwidth is less than x of t. It's half of x of t, you can say. Right? So we would be interested to find out this signal. Well, to find out this signal, because we will deal with the passband signal. So our example of we will take the passband signal, which looks like this. We assume that our passband signal, which has just half of the bandwidth, right? The passband signal having half the bandwidth, Suppose this is the passband signal, a real signal. In the passband we receive x of f, right? X of f, and we are interested to find out. Now this is a real signal. It has the negative part as well. This is the signal which we would receive at the receiver side. So the receiver receives this passband signal. It's a real signal, and usually this is a very high frequency, this f0, maybe of you can say in gigahertz. So you cannot process, your electronics does not usually work at such a high it can work, but you need a very sophisticated and expensive circuit to extract your signal from this higher frequency band. So instead of processing the signal in this higher band, we would like to down convert it to the baseband, and then we would process that baseband signal. At the same time, we are only interested in the positive frequencies x plus of f, right, which contains all the information of the transmitted signal. So we would like to derive the equation for x plus of t, right? What this looks like. So we will do it in the after the break.